Okay, so now let's discuss the co-area formula. Okay, so well, this is a simplified version of the co-area formula, but okay, so consider a smooth function u from the manifold into the real numbers, and by Sard's theorem, the critical values of u have zero measure in the real numbers, and so let's just go ahead and assume that u is proper and that the inverse image of all the critical values of u forms a closed subset of our manifold. Okay, and without loss of generality, if we want to integrate, um, so the idea would be we want to kind of change variables and look at the vector field, which is given by gradient of u divided by the norm squared of the gradient of u. And we want to integrate along the flow of this vector field. And essentially, this will allow us to construct a foliation of the manifold into level sets given by the inverse image um, of like points in R under the map U. Okay, so essentially, we're having U be this smooth map. We're going to decompose the manifold M into the level sets of U. So perform a foliation of a one parameter foliation of the manifold. And then we want to kind of perform a change of variables to understand how do we integrate a function over the manifold by basically disintegrating with respect to this foliation. And so the co-area formula says that, okay, well, let me just state the formula. So essentially, we have that the integral of a function f over the manifold times the norm of the gradient of u, so the absolute value of the gradient of u, integrated against the Riemannian volume element over the manifold, is equal to the integral over the real numbers, um, um, and then integral over these submanifolds of which are the level sets of, let's say that our real number line, let's use the letter t to denote the coordinate of this real line. So the integral over r dt, and then the integral over the submanifold u inverse of t, um, the integral of that submanifold of the function f integrated against the induced Riemannian volume element on the submanifold. Okay, so essentially, in order to disintegrate this function f correctly, we actually need to add a scaling factor, which is the norm of the gradient of u, into the left-hand side of our formula. So integral of f norm gradient of u dv is equal to the integral dt integral of u inverse over u inverse of t of f integrated ds of t, where ds is the the volume element of the hypersurface, which is the level set of the function u, and it's the Riemannian volume form induced on that hypersurface. Okay, so the question is, where does this formula come from? Well, there's a couple ideas. So first of all, if you look at the function u and look at its gradient vector field, okay, so the gradient vector field is kind of the direction in which u is changing the most rapidly. Okay, so if we look at the codomain of u, so the codomain of u is just the real number line, and if we perturb, let's say we're at a point t on the number line, let's say we increase to a point t plus dt, then if the gradient of u is very, very large, then this perturbation in the small perturbation in the codomain is going to produce a tiny change in the level set u inverse of t. Right? But if the gradient of u is very small, so u is not changing very rapidly, you could think in one dimensions of like the graph of u where t is the y coordinate, and let's say Rn is the x coordinate, then if that graph is almost horizontal or has a very small slope, then all of a sudden the inverse image of a small interval is going to have a very large volume. Okay, so in fact, the rate of change of the volume of like u inverse of negative infinity to t, the rate of change of that volume in the manifold is actually given by the integral over the boundary um, of this set u inverse of negative infinity comma t. The boundary of that set is just u inverse of t, and the integral over that hypersurface of 1 over the gradient of u dst, right? And so basically, if the gradient of u is very small, then the rate of change of the volume of uh, the cumulative volume u inverse of the interval negative infinity comma t, that volume is going to be changing very quickly if gradient of u is small, and vice versa. If gradient of u is very large, then the cumulative volume traced out by u inverse of negative infinity t will be increasing at a very slow rate. Okay, so then the idea behind the proof of this co-area formula is essentially we want to calculate the metric, or this Riemannian volume form, in terms of the local coordinates, where we choose a local coordinate system which is adapted to the flow of the gradient vector field of u. Okay, so you consider the gradient vector field of u, and we're actually going to divide the gradient vector field of u by its norm squared. That gives us a vector field, and that vector field has a local flow. Okay, now it turns out that if you take the derivative of u composed with the local flow of this vector field, the time derivative, then you actually get it's identically equal to 1. All right, and that's because of this calculation where if you take the time derivative of u composed with phi t, where phi t is the local flow of the vector field grad u divided by norm grad u squared, then this derivative is just the differential of u applied to the vector field, which is given by grad u over norm grad u squared. The differential of u applied to that vector field is just g of grad u, g of grad u, comma grad u divided by norm grad u squared. So it's just 1. So that gives us a uniform kind of a uniform rate of change of u along this flow, which is given by the vector field grad u divided by norm u squared. Okay, and so we take this vector field, then we can use this vector field, let's call it x, to that vector field is going to be one of the elements of our basis in our coordinate frame, and then the other elements of the basis are just going to be some basis vectors which are tangent to this leaf of the foliation u inverse of t. All right, so basically if we do this, then of course since the vector field x is pointed in the direction grad u, and all the other basis vectors belong to the tangent space of the leaf u inverse of t, then these vectors are going to be orthogonal. Okay, and so if we look at the volume element, it's going to decompose into essentially it's going to decompose into the volume given by the square root of x inner product x, and then multiplied by the square root of the determinant of this of this um, 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 the tensor components in local coordinates of the frame of the leaf. Okay, so these n minus 1 coordinate vectors which span the tangent space of the leaf, the determinant of basically the induced Riemannian volume form on the submanifold given by the leaf, that determinant, the square root of that determinant multiplied by the square root of the inner product of x with x, okay? And the key thing here is that we now can use this time coordinate t as essentially one of our coordinate directions of the manifold, and the flow induced by this vector field x is equal to grad u over norm grad u squared is exactly the flow that we want to use in order to get the right uniformity in our time coordinate to perform the integration with respect to the Lebesgue measure on r given by dt. Okay, so if we take this square root of x comma of the inner product of x with itself, what do we get? Well, we just get 1 over the square root of 1 over norm grad u squared, which is just 1 over the norm of grad u, okay? So we get 1 over the norm of grad u. That's the scaling factor, which is applied to this Euclidean length element dt, where we've decomposed the metric into, the metric on the leaf, the induced Riemannian metric volume element on the leaf, u inverse of t, and then this length element, which is uniform in time, given by 1 over norm grad u dt. Okay, so then if we look at the integral of the function over, if we take an arbitrary function practically supported of the manifold, okay, and we go ahead and perform the integral of this function with respect to the Riemannian volume element, well, if we want to integrate along this, if we want to integrate, let's say, along this foliation, then let's decompose the Riemannian volume element as we just did. When we decompose the Riemannian volume element, we see that we get a factor of 1 over norm grad u dt in terms of the temporal integration. So in order to reconcile this, we just have to scale f by a factor of norm grad u. So we get that the integral of f norm grad u dv, where v is the Riemannian volume element, that is going to be equal to the integral over dt of the integral over the leafs of the parameterization u inverse of t, f ds of t, where ds of t is the volume element of the hypersurface given by these leaves. Okay, so this is called the co-area formula, and it essentially comes from decomposing the Riemannian metric in terms of this coordinate basis, where one of these coordinates is in the direction of grad u, but of course needs to be scaled by the vector. It's actually the local flow of the vector field grad u divided by norm grad u squared, and it's scaled in this way such that the local flow has a uniformity in time, namely the derivative of u precomposed with this flow is identically equal to 1. So yeah, that gives us the co-area formula, which allows us to integrate a function against a specific foliation of the Riemannian manifold into leaves, and that foliation is determined by some smooth function and its level sets. Okay.